This video is on the analysis of SDS page images, and such an analysis is carried out to determine apparent molecular weights of proteins that are resolved as individual bands on an SDS page image, which I produced during the video on the technique using SDS page and the banana extract sample. This gel was stained with catechol, a simpler version of a diphenolic compound. I also used dopamine and 4-methylcatechol, but the catechol stain gave the best resolution. In lane 1 of this cutout piece of a larger gel, you see the protein standard or protein marker. For the protein marker, we know the molecular masses. These numbers should all be given in kilodalton, so ranging from 180 to the very bottom 15 kilodalton. The sample loaded in lane number 2 was the crude extract. It's not a purified protein, but if we stain with catechol or any other diphenolic compound, we specifically stain proteins that show polyphenol oxidase activity. Note that in a crude extract, you have many other molecules present. For example, other diphenolic compounds that can form quinones, that can attach to a protein, or that can form the formation of larger molecular weight species towards the top of the gel. You can also have protein damage or protein decay in the form of losing some pieces of your protein, and that might have happened to the smaller piece that you see here on the bottom. So to evaluate the gel, we first focus on the standard, and for the standard we need to determine the retention factors or relative mobilities. I'll first try to measure the migration of the dye front, and to do so I'll insert an object from the illustrations, and I'm going to choose a rectangle shape, and I'll start to draw the rectangle at the top where the sample was applied all the way to the middle of this dye front, this feature right here. I can zoom in to help me position the top of my rectangle to exactly the loading well. And the lane ran a little bit crooked, but I think I'll capture the middle of this dye front fairly well. The length of my rectangle is the migration of the dye, which is 3.45 inches. These standards have a range of different molecular weights. They're given in kilodalton. I probably should have said molecular masses given in kilodalton. And the values range from 180, 130, and one by one, I'll determine the migration. Again, I'm going to insert as an illustration one of those rectangle shapes, starting at exactly the same position for the loading well, and then going to the middle of the darkest spot of my band. And the length here of the migration for this band was 0.96 inches. I can now work my way down all these standards, trying to position in the middle of the darkest region of the band to be consistent. Shape format then gives me the length 1.09. If you have a piece of paper, you would do the same technique with a ruler. .34. And speed up the process or speed up the video. This one is a bit iffy. I'm just going to go to a similar region. 1.65. And 3.39. To calculate the RF value, all you need to do is take the ratios of the migration distance of your standard band, and you always divide by the migration distance of the die. So by pressing F4, I can lock the migration distance of the die, which was 3.45 inches, in place. To make a graph, I need the log of the molecular mass in kilodalton. So it's going to be this whole row. And then I'm making a graph to see if I have a linear relationship or if it would be better to use an extrapolation. It's not necessary to have a short title, but definitely you need the axis labels. So on the y-axis is the log of the molecular mass in kilodalton, and on the x-axis is the relative mobility, or the RF value. We can already see that our trend line is far from being a perfect linear arrangement. The R-square value still looks decent, but several of our points deviate, especially right here in the beginning, but also unfortunately in the middle region of our trend line. And in this region, we have bands that we are later interested in. So the two bands that I want to know more about are the two most prominent bands. So I'm going to decide to analyze the position of this band between the 35 and 40 kilodalton marker and the band that is the smallest molecular weight band between the 25 and 35 kilodalton marker. I'm going to call the first band band 1 and the second band band 2. The die front will be fairly similar, so if I insert a shape to see how far the die front migrated here, the middle, so this is 3.43. Oh, sorry, 3.46. So die front lane 2. And the individual bands I'm going to color code the wrong direction. So this would be the start of the lane. And I think I hit the middle. It's 2.3 inches. I'm going to insert another shape. This band. Maybe orange and no fill. Maybe towards the middle of the band. 2.78. Inches is the migration for this band. Maybe I want the numbers over there. So the first band was colored, or the second band, I still have the orange color here, and the first band was the one marked with green. The RF values, again, are just the ratio between how far did your protein migrate in relation to this die front. So protein divided by die front. And as expected, these RF values fall between the standard RF values. We could use the trend line to make an estimation, but the region that we'll want to investigate with the RF values 0.66 and 0.80. In this region, we have a bit of a deviation between our data points from the protein standard and the line. The deviation looks small and the R-square value doesn't look too hideous, but you have to keep in mind that this is based on a log, and later when you do the anti-log, like 10 to the power of the number you obtained for the log, you have a lot of leverage at this exponent. Therefore, any deviation that you have will have a huge influence on your final number. The final number is your estimate of the apparent molecular weight after using the log value in the exponent. But for an estimation, you can say estimated based on trend line. So the log would be taking the RF value, multiplying it with the slope, which was minus 1.4056, and then adding the y-intercept 2.5651. Then the molecular weight itself is going to be 10 to the power of this number that we just estimated. So this would be estimated molecular mass in kilodalton. 43 kilodalton is a surprising outcome of this estimation because your band is positioned below the standard, and we would therefore expect a number that is below 40 kilodalton. So that's a shortcoming of this type of analysis where we use a linear trend line and the fit is deviating, or our data deviates from that linear trend line. So in this case, it would be better to use a extrapolation, only using the two closest data points and then focusing on extrapolating the estimation of your molecular weight between these two data points. For band 1, therefore, we will focus on this data range here for the 40 and 35 kilodalton. And for the other band, band 2, we will focus on the lower impact. For band 1, we therefore focus on the data highlighted in green, and for band 2, we will focus on the data in the box between 25 and 35 kilodalton. So extrapolating between 35 and 40 kilodalton. So we can get a slope just focusing on these two data points. We need the log and the RF. And we also need a intercept. So intercept, I misspelled. And this estimation, I can take the same RF value, but I'm multiplying with the slope that came from just two data points, and I'm adding the intercept that also came from just these two data points. And then if I do the anti-log, I'm getting a value of roughly 39 kilodalton. So that seems much more appropriate because it must fall below the 40 kilodalton line. The second extrapolation again, we calculate a slope of the log of the molecular mass versus the RF value. We also calculate an intercept. Just want to check if I use the correct value pairs. Yes. And then using the RF value with this new extrapolated slope and the y-intercept gives me a new log of the molecular weight that I estimated. And to get the actual estimate in kilodalton here, now the estimation would be 30 kilodalton. Still, these are only estimated apparent molecular weights, not exact molecular masses as you could determine, for example, with mass spectrometry would be a superior technique to get to a molecular mass of a purified protein, but for a rough estimation of an apparent molecular weight, this technique is fairly fast and therefore useful. Our value of 39 kilodalton is within the vicinity of the banana PPO value, but still, as you'll see when we discuss sequence alignments in the joint Zoom session, these numbers could still come from a truncated form of PPO, so we need more information than just these apparent molecular masses from an SDS PAGE gel to make conclusions about the overall size of a protein like the polyphenol oxidase from banana pulp. So till next time, and have a good day.